Hello, everyone. My name is Dr. Daryl Chamberlain Jr., and I'm an educational data scientist in the Department of Mathematics, Science, and Technology. My research focuses on applying theoretical learning trajectories and machine learning algorithms to analyze, anticipate, and describe student thinking in the mathematical sciences. I take a multidisciplinary approach in my work. I use theoretical frameworks from cognitive psychology to qualitatively describe student thinking. I use my content knowledge from my PhD in mathematics and statistics to theorize how students might develop advanced mathematical concepts and how that might evolve over time. And I even use my expertise in programming languages to implement machine learning algorithms based on both of those other two approaches to implement dynamic feedback to students based on how they're answering questions, rather than just something like they got a question right or wrong. But that was kind of a lot. So let's break it down. For example, psychology-wise, we have a general understanding of how humans initially learn a concept and then how they build on that concept. So I can take that generalized understanding and apply it to some mathematical concept, like infinity. There's a very rich history of how humans in general have developed their understanding of infinity over time. So, based on that, based on some other key insights that we've had in the mathematics community, we can set up some kind of hypothetical learning trajectory. This is a way a student might think about infinity over time. And we have a lot of these based on what might happen as this path might branch at a bunch of different important points, like which classes they're taking. So, based on some key phrases and other indicators that a student might say, do, show while a researcher like me, we're talking with them, a machine learning algorithm can try to predict where in this hypothetical learning trajectory for infinity that the student might be, and then, based on that, provide some kind of feedback to get them to that next step. This is the next level of how we're going to push education forward. Rather than just saying you got it right or you got it wrong, go to the next question. It's more about what did you say? Let's think about the meaning of what you said. And then let's respond in an intelligent way, not in a chat GPT trying to just use what other people have said, but really a method that is understanding what the student is saying and trying to respond to that understanding. As you might guess, this type of work looks very much like the basic scientific method. I make some evidence-based hypotheses. I start and complete a learning experiment where students use this magical technology that they interact with in order to predict their thinking and then analyze whether it worked or not. This analysis is actually both qualitative and quantitative in nature. Think of it similar to image processing, where you have some machine learning algorithm is in the background. You present the machine with a fruit, and the machine says, okay, using its visual software, can analyze that it has a reddish hue. It's, you however many centimeters tall, however many centimeters wide. So the color is qualitative. These measurements are quantitative. And the machine learning algorithm is going to take both of these indicators with a few others and say, aha, that's an apple. That's kind of what I'm doing with students' understanding. I'm taking their gestures, their facial expressions, the intonation of what they're saying, and even exactly what they're saying, how many times they say it, whether something's there or not. I'm using all of this to try to predict what they're thinking about for some concept. So, as you can see, my department, Mathematics, Science, and Technology, is perfect for me as my research combines mathematics, science with the cognitive psychology and the technology aspects to improve the learning experiences for our students.